Right. So we converted this formula into a different form, I should say, right? Because just for convenience, to avoid multiple measurements of other isotope ratios, and also we can avoid having some issues related with the uranium thing, because sometimes it can be open. I mean, the system can be open during the evolution. So just to avoid such kind of problems, these two equations, since we have two equations from the uranium lead system, it's convenient that we rearrange it in another form. And luckily, we are having some fixed value, such as uh, uranium 235 to 238 ratio, right? Which is 1 over 137.88. So we can directly apply that number there, and we can reduce further unknowns. So the amount of radiogenic production, that means 207 amount, is denoted as 207 lead star, and the same for 206 star. The ratio we can interpret according to the below formula, right? So you can see clearly this newly rearranged formula give you some certain values here. For example, for this value, right? So it's very convenient for us, right? So now we have a sort of a new formula, or a rearranged formula, where the amount of radiogenic production, both 207 and 206, because these two are resultant from the two isotopic decay schemes that we have from uranium lead scheme, right? So the ratio of that is equal to this value, and here we know this ratio, which is a constant. So we know lambda, right? It's experimentally determined, and lambda 1 and lambda 2 both we know, right? So only unknown is T, and we can have this equation very useful as a very useful equation for age calculation, right? But of course, we don't know some values. For example, uh, the 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 real values uh, for this entire thing. So therefore, what we are going to do is we try to make a graphical representation of this equation. We make a graphical representation of this equation, so that I will show you how we can do that, right? Okay, so look here. This is the new formula that we have, right? This is the new formula we have. Uh, just a minute. Right, so we have this new formula uh, which contains clearly identifiable values. For example, lambda 1 you have, lambda 2 which are known, the unknown is T, right? Unknown is T. In case if we do not know uh, these radiogenic amounts, so now there will be a problem, because we do not directly measure this ratio from the machine. So that is the only problem we face practically when using this equation. So that's why we have to use this formula in a graphical form, right? Because the normal ratios that that are measurable are these ones, right? So these are the ratios that are directly measurable, right? Sorry, this is the initial one that we have to calculate, not this one, but the present day values we can measure, right? 204, 206 over 204 or 207 over 204, right? These are measurable. But now, since we have eliminated some of the terms there and also converted this equation into another form, we are left with 207 lead divided by 206 lead. This is not directly measurable from the machine. So therefore, again, we have a practical problem, even though we sort of simplified the previous equation into this form. So that's why we want to use it in a graphical form, so that we can find another type of a solution uh, where we have two unknowns but we are left with only one equation, right? So this is also unknown now. T is also unknown, right? So apparently there are there is a difficulty in solving this one, right? Because two unknowns, only one equation. Although we wanted to eliminate some other parameters that are giving us some troubles during the evolution of the materials, but now we are again facing some other difficulty where we don't know two unknown variables are there, right? So to avoid, to solve that, what we have to do is we go for a kind of a graphical method, right? For that, first we need to formulate a table, right? First, we want to make a table, because you can clearly see that algebraic solution is not available for this one, as there are two unknowns, right? So we make a table, right? Make a table with what? We take these values for different values of t, right? For different values of t, you can make these values, right? A table, sorry, a table you can produce with different t values corresponding to different t values. So let's see how we can do that. Okay, right? So here, so you can choose arbitrary t values. That means the time. T means the time, right? So you can take just arbitrary values starting from even zero, right? Starting from zero, you can start from zero, no problem, right? From there, you can go up to even the age of the Earth, because we are interested in materials, Earth's materials. That means the time span should be from 0 to 4.5 billion years, right? So there you can go up to this age, right? So these are the arbitrary values that we choose, 4.5 billion. In the middle also you can stop, but the perfect graphical solution should have 0 to 4.5 billion uh, year time duration, right? So how we can do this? So you can insert different values of t from 0 to different values that we chose for t, right? You can replace those values. You can substitute these values here, and you will end up with some final value here, right? Once you put t here, you will get a value for this ratio, right? Because lambda 1 and 2 are known. So directly you can apply lambda 1 and 2 values there, and then multiply by 1 over 137.88. So that will give you some solution, right? Some answer. That answer will be equal to this ratio. Okay. So you will get some value. So for each corresponding t, there is a value, right? So this is it. So for first term, for this one and this one, you have two terms. The first one you have here, right? You put t, different t, for example, 0.2. This is billion years, 0.2 billion years, okay? Here, 10 to the power 9, that means gigaanoms, right? So 0.2 billion years, you put that there. Then you will get some value for this term, right? Some value for entire term, right? Entire this term. And you can substitute t here also. So basically, you will be getting this term and this term, different values corresponding to each of these time numbers, time values, right? That will be if you put that, I mean, if you multiply that division of this one and this one, multiplied by 1 over 30, 137.88 means you are getting this radiogenic ratio, right? So corresponding ratio for this value should be 0.05012, like, right? This is the value. So that means you can fill this table, right? You can fill this table. You just want only these age values, arbitrary age values. So you can start from 0 to 4.5, right? You can start from 0 to 4.5, and then you have a series of results, series of values that will give you this ratio, right, as the radiogenic ratio. So actually this is a kind of a universal type of a graph that we are producing, because this represents the entire time span of the Earth. That means from 0 to 4.5 billion years, together with the corresponding ratios for all possibilities of corresponding 207, 206 ratios, uh, with lambda 1 and lambda 2 substituted there, right? So each isotope system will represent here, I mean, uranium 235 and 237, those two isotopic systems will be represented in these two, right? So what you get here is 207 ratio and 206 ratio, which is the radiogenic component, right? The radiogenic component. If the rock evolved from like zero point 0.2 gigaanoms ago, right? If it evolved from 0.2 gigaanoms, that means if the age of that rock, particular rock is 0.2 GA, right? Then in that rock, definitely you should have radiogenically produced 207 over 206 this much. Understand? If your rock is 1.6 billion years old, this rock today must have radiogenically produced amount of 207 to 206, this amount, right? According to this equation, because this equation was derived one, so which is derived from the natural radiogenic two equations. So therefore, it should be correct, right? This ratio should be correct, right? So correspondingly, you have these two terms also. Then what you are going to do is, you can just remember back the previous occasion where we derived this E lambda 1 t minus 1 from where? From this radiogenic decay, right? Do you remember that? Where is that? You must have it, right? See, 238, 206, 235, 207. So these are the two systems that we took. So the amount of radiogenically produced isotope ratio quantity should be equal to this one. So this one will give you the radiogenically produced amount, right? So what you are getting here is, this value, right? 206, 238, 207, 235. Okay. So this is the radiogenic amount. This is the radiogenic amount. So again, you can just look into your previous equation, and then you can realize that that is the amount, right? So don't get confused. You see here, again, I want to show you this one. Yeah. Okay. So 235, 238, and 235, right? Just forget about 204 normalization. Just forget about this normalization. This was just normalized for our convenience, right? To measure to give the value as measured ratio. But you can just forget that and relate this component so that you will be ending up with this term. So you can do that this by yourself as a self study, and you derive all this each and every term. Okay, right. So this is equal to 206 lead over 238. That is the radiogenic product, and E lambda 2 should be equal to 207 over 235 uranium. Okay, the radiogenic component. Right. Now, what we are going to do is we have these two values. That means you have this value here and you have this value here in the table. So what you have to do is now you take, because we are going to make a graphical solutions. We are going to make a graphical solutions. You take them as x and y. You take these two values as x and y, right, of this graph, right? Because we arbitrarily changed t and came up with some set of values. Since we had the two unknowns in the relevant equation, right? So we opted for a graphical solution. Okay, so that graph will be like here. So you can see 207, 235, right? That means this one, right? This one. And you have 206, 238 here. That means this one. So these two is now plotted here. So you are getting a curve like something like this, right? So this is a natural variation curve, because for different t values, that means from present to the time of the Earth's uh, origin, right? Earth's accretion, origin time, with the real numbers for decay constants, we made some table with values that should represent naturally produced amounts of radiogenic material, right? So that is a very unique feature of this uranium lead system, since we are having two isotopic systems, two decay systems for a one material, right? That is we are getting 207 as well as we are getting 206 from the same material, right? Two decay schemes are there. Thorium is separate. We are not putting thorium into here. We take just only the uranium two decay schemes, right? So that two decay schemes and the corresponding values of the ratios, that means the radiogenic amounts of 206 and 207, which is given by E lambda t minus 1, E lambda 1 t minus 1, and E lambda 2 t minus 1, right? These values. So it will provide you a kind of a universal type of a graph, right? Universal type of a graph, because we didn't care about any material here, right? We did not want to specify anything here, whether it is zircon or monazite or feldspar or anything, right? It can be anything, but lead is lead, right? Wherever it present, it is lead, right? So the way of decaying is unique for that system. It doesn't, it is not controlled by the hosting material. So therefore, no problem. We can use this as a universal graph, right? So that is a plus point for uranium lead system. So we have a now very fixed graph, because starting from zero, irrespective of the material, whatever the material that you are concerned, doesn't matter, right? Because we don't have any other parameter for this equation. Do you have any parameter for this equation? Any other parameter? No. What you have only is the decay constant, right? That is unique for each decay scheme. 238, you have a unique value. 235, you have another unique value. So those are the only things that we have, which is different for any material, right? T we arbitrarily inserted there, that just to cover the entire time span of the Earth. So irrespective of the material, what you are analyzing, if you are interested in measuring this or getting this ratio as the radiogenic product, which you can't measure by a machine, that's why we are going for a graphical method, right? So you will get the same graph, right? Because only t is different, no other thing is changing. So therefore, whatever the number you put here, you will end up with the same values, because lambda 1 and lambda 2 are fixed numbers, right? So that's why we call it a universal graph, right? Actually, this is a universal graph, but we don't call it as a universal graph, but we name it as a Concordia diagram or Concordia curve. The name of this universal type of graph is called Concordia curve. So this is a curve, right? This is a curve. It's not a linear variation. It's a curve. So you can see here for this is actually these gradations means the time that we had from in this table, this set, these values. You can have these values in on the plot as graduated bars on the graph itself, right? And corresponding x ratio, corresponding y ratio at a given time, right? So you put you mark the time there, right? Because for x and y axis we take these two ratios, right? These two terms, and corresponding t value you mark on the graph, because these are this is universal, so it won't change, its position won't change. So that means if 3GA time, then the corresponding 207 to 206 uh, ratio, or this one, sorry, corresponding 206 uh, 206 to 238 and 207 to 235. That means these two values will be uh, not changing, right? It won't change. So for 3GA, it will be like this, irrespective of the material, because it won't change based on the material, right? So you have corresponding values. For example, for 4GA, you have a corresponding value there, which is material independent, right? Material independent, as long as we have used the precise decay constant, lambda 1 and lambda 2. Those are the only things that can change the Concordia shape, right? Sometimes, when some experiments are being conducted on research purposes, there may be slight changes for the Concordia, changes for the decay constant, right? So that might make slight changes in the Concordia curve, but in that case, you have to use the relevant reference there if you are using that particular Concordia. But nowadays, you don't have to bother about that, because we have standard Concordia curve. Uh, so we can use directly that Concordia curve, right? So multiple, oh, that means hundreds of time values and corresponding ratios, 207 and 206 ratios have been utilized to make a very precise curve. Because if you use only one, two, three like measurements, when you it's kind of an interpolation, right? When you interpolate these points, you may do a lot of mistakes, right? Some bending can be there, some uncertainties can be there, like that. But if you have thousands of points, right, like this, if you have thousands of points, very close by thousands of points, then you can have a more better curve produced along that points, right? So this is done using computers. So you will definitely be using a computer for edge derivation if you are using a Concordia diagram, right? Manually doing is also possible, but it carries a huge uncertainty because between the you see the space between these two. This is 3.4 and this is 3.6. So that means only 0.2 giga-nm difference there. But if you take an area like here, the difference is very tiny, right? The difference is very tiny, and even it's smaller than the dot size, right? So you have a dot here, maybe smaller than the dot size. So there is a big issue about the accuracy, right? And when it comes to the old ages, the spacing is much higher so that it is easy for us to manage. But because of this inhomogeneity in this curve, that's why actually this type of a curve has been produced. We can use computer softwares or programs to find out whatever the date that we are interested in, because after measurements we can convert our we can find our radiogenic amounts and this ratio by the machine, right? Although we can't measure directly 207 to 206, right? I said that we can't measure directly this one, right? We can't measure this one directly from the machine, right? But you can measure directly this value you can measure, right? This is 207 to 235, this is 206 to 238. So that means these are obtainable values. You can take them, you can find, you can get them from the machine. So that means you will have a set of data, right? And you can tabulate them, right? You can tabulate them, and you can tabulate them, one here and the other one there, right? And you can plot. So what you are going to do is you take a template of a Concordia plot in a software or in Excel, right? And then on that graph you plot your ratios, right? You plot your ratios. So you have a reference graph here already, right? Reference graph is there, that is the Concordia plot, right? You don't need to draw any curve using your data points. You have already template, right? You have this template, and on top of that you plot, just you plot these your values, right? Then in some places you can see your sample exactly lies on the Concordia. Sometimes it's deviated from the Concordia, sometimes it's very closely spaced with the Concordia. So there are different interpretations for this type of things, right? So we have to plot anyway, so and plot and see, right? The better accuracy will be there if you have more and more number of analysis, right? Even for single rock analysis, it's important that you do it in multiple samples, right? So in that case, if for example, if one value is here, the next value may be here, another value may be here, another value may be here, so that you can have this entire cluster as your isotope composition of that particular sample, right? Sometimes you might see some of the values are very much deviating from the Concordia curve when you plot, right? So that means they have some problem. That means some assumptions that we have may not have been fulfilled. For example, the system might not have been in as a closed system, right? Or otherwise there may have some reactions taking place in those samples, right? So anyway, disequilibrium, right? If the system has been open, this type of things can happen. Actually, ideally, it should come over here to the curve, because if that rock was crystallized at 4 GA, the measured value must lie on this graph at here. But due to some reason, your point deviates something like here. So that means your data is not concordant If it is exactly plotting like here on the graph or very close to the graph, very close to the curve, you call it concordant. Concordant, right? Previously also we used that term. Concordant means the age is very unique, constant, right? But if that point deviates from there, from the curve, that means you see here, it's deviating much. Sometimes it can be deviated upwards also. There are possibilities. So we call them discordant, right? So in an analysis, you might have a set of concordant values as well as set of discordant values, right? Usually we apply this uranium lead isotope system for zircons. So all the discordant values that you get from some zircons means that those particular zircons were not kept as a closed system. That is the most possible way of explanation. Not as a closed system means they are lead uh, or uranium, or yeah, here uranium, not thorium. Uranium or lead may have exchanged with the outside of the system, right? So in such cases, you will have discordant analysis, discordant points. Actually, some situations, if this discordance is very systematic, if this discordance is very systematic, that is also useful, right? So being discordant is also useful in some cases, right? So we will discuss about that later on. So anyway, this is what we learn as a Concordia curve. Is there any question related to this section so far? Do you have anything to ask? So remember, this is a kind of a universal curve. That means you can use this curve as it is, and you analyze with your samples. You get the values from the ICP-MS or whatever the instrument that you are measuring isotope ratios, and plot that, right? On top of this standard graph, you plot them. So this standard graph is called the Concordia diagram or the Concordia curve. Okay, so you are having this Concordia diagram which has graduated points, right? So we discussed how these graduated points are taken, right? This is actually coming from this table, right? These points are coming from this table. So this is the basic or the preliminary table that we wanted to construct to make this graphical representation of these ratios. Okay, right. So it's like if you get a sample, for example, okay, I'll put that you measure some sample, rock sample from Sri Lanka, and maybe your sample plots over here, right? When you measure that, you have X and Y, X and Y values, X and Y values, that means 207 and 206 values. Corresponding to these numbers, right? So what do you think about this sample? What can you say about this sample? It is directly plotting here. That corresponds to an age like 3.1, isn't it? Time graduation or the time should be interpolation. If you interpolate this in between these 2 points, 3 and 3.2, so you are exactly in the middle, right? So that means 3.1. So the age of your rock is 3.1 G, right? So it's very interesting graphical type of a representation, but it's very precise because this Concordia curve is very precise, very precisely determined by thousands of values like these ones, right? So numerically processed, and this very smooth graph has been constructed. So if some isotope ratio you have, if it can be matched with some value here, so that value should exactly corresponds to its crystallization time, right? So this is how we get the age from a Concordia diagram. Actually, there are there are because we are dealing with multiple samples, right? Maybe 30, 40, 50, or 100, even more than that, right? So in that case, you will end up with so many points, right? So many points which are very, very complicated also, because from one sample you may have 50 points, another sample maybe 100 points, some are overlapping, right? So it will be very, very crowded, very, very difficult for us to manage manually. So that's why we have to always use computerized software or a program based on Excel, right? So the one that I mentioned in the class as Ludwig's Excel sheet, that can provide you these Concordia diagrams as well, right? So what you have to do is you have to put your values. Raw values means the ratios that you get from the machine. uh, Actually, even from the machine you are not directly getting this ratio, right? You will get the other ratios that you consider, 207 over 204, 206 over 204, those values. But by the software itself, that will be converted into this ratio, because this is a special ratio that we are considering for Concordia diagram, right? So even though I said that you can get these numbers from the machine, it is not directly given, right? First, you get some ratios of 206, classical ratios, 206 and 207, normalized to 204, like, and then it will be converted into this form, right? So these numbers then get plotted in this on this template or on this Concordia diagram, so that you can find corresponding ages for your different samples. Okay, so we normally regard the Concordia diagram as a plot of 206 over 238 ratios versus 207 over 235, right? So all radiogenically produced amounts. So we are considering only the radiogenic component, right? So that's why we took only this term, right? Because this term corresponds to radiogenic production. Okay. Right, now you have the Concordia diagram, and you have some fair understanding about the Concordia diagram, which you can easily use for dating of your rocks, right? So this is a graphical representation, but although this is a graphical, this is a very precise type of a calculation. I said that your sample may contain a large number of points, right? So we call such a set of points as a cloud or a cluster, right? Or cloud or a cluster, right? Cluster, cluster. So this cluster, again, you have to statistically process, right? You have to statistically process this cluster and get the mean value as the age, right? Because you have so many ages even within the cluster itself, right? 3.4, 3.41, 42, 415, 434, like that. There may be so many values also here. So it will the statistically you have to process this cluster itself, only each cluster separately processed, and then you will get a age and also an uncertainty as well, standard deviation, also plus or minus value, right? So this is how you get the age of a, particular sample. So at least 10, 15, the more is better, right? At least 10 points should be there. That means you need to have at least 10 zircons to get a meaningful age from a rock. Of course, there are thousands of zircons from a small piece of rock, like granitic or some felsic rock. But mafic rocks contain very limited amount of zircons. There, you will have only few zircons, maybe, right? So in that case, still you can give it, even from one zircon, you can give a given age, right? But the precision may be questionable, but nothing to do. I mean, we can't do anything because for mafic rocks, there are always less number of zircons there, right? Anyway, repetitive analysis. Even if you take one zircon. For example, this is a zircon, right? So you can choose 5 micrometer areas to analyze. So that means you can analyze even 10, 15 points inside the zircon, tiny zircon. This is 150 micrometer zircon. So inside that, 5 to 20 micrometer space is enough for one analysis, one spot analysis. We call spot analysis. This is a one spot, second spot, third spot, like that, right? So you can have even 10, 15 analysis data for a one zircon also. So that means at least you have repeated measurements from one each circle, right? But similar measurements, there may be so many similar measurements from other zircons as well. So at least 10 or 20 zircons you are using, and inside also you have multiple measurements, right? So that means statistically fair amount of data distribution you can expect from your sample analysis. So that means you will be getting a much reasonable value, reasonable age, right? So this is what you call the Concordia diagram. So we have to use this Concordia diagram if we are so if we are utilizing the uranium-lead isotopic system for our dating purpose. Okay, any question up to now? Can you please uh, put your registration number into the chat box, because I want to mark the register attendance. Okay, right. Then these Concordia diagrams, they are very much common, frequently used for plotting radiogenic uranium lead data from analysis. Because they are very much precise. The data, I mean, the dates given by Concordia diagrams is very much precise, because you have tens of points even for a single zircon, right? You can have multiple points. So that means more fair value, more fair analysis you can expect, even statistically reasonable analysis. If you consider the rubidium, strontium, or samarium, neodymium, one analysis from one sample, right? Of course, we need multiple samples, but each sample will give you only one data, right? So within that one sample might be very much heterogeneous also. In that case, it's very hard for us to make them the data which is very how to say, very homogeneous data, right? We can't expect that they are very much homogeneous because the rock sample might be heterogeneous, right? Some places might be having for example, if you had garnet-like minerals there, it takes a lot of volume there, right? So when you calculate the model percentage, you know how difficult when garnet is there, right? Even a single garnet can cover entire your field of view of the microscope, right? So then you will be in trouble because you can't give 100% for garnet there, right? So you have to consider the overall presence of garnet. So likewise, there may be heterogeneities from one place to another. So that means if you are taking three samples from one, three representative samples from one single rock, you might be getting three values, different values, right? If it is not homogeneous, right? So that is avoided in this case, because we are taking even a single zircon we can take, but we can take multiple measurements with that even tiny zircon, right? 100 or 150 micrometer size, very tiny. Okay, right. So the isochron diagrams utilize only one decay scheme. That is another disadvantage, right? Here we have two decay schemes, right? For uranium, of course, we have three, but altogether we can, for the Concordia diagram, we can take two decay schemes for the same sample, right? So it's like a very controlled type of a behavior, right? You have x-axis variation, you have y-axis variation, but both variations are resulting from the same sample, right? So two decay schemes are there, for each point, unlike the isochron diagrams. Okay. And uranium lead Concordia diagram, we have another one here with an example. You see here. Okay, you see here 1, 2, 3. 1, 2, 3. You have 1, 2, 3 there. Okay. So 1, 2, 3 there means you have three data points. Exactly plotting on the curve itself. That means on the Concordia itself, you have the data points. So how can you explain their behavior? They are 100% concordant. They are 100% concordant because they are exactly plotting on the Concordia curve. They are not discordant. They are concordant. Right. So this is these 3 points will give you 3 separate concordant edges. Right. 3 separate concordant edges. That means three timings. Right. If those are representing 3 zircons, these 3 zircons should represent different individual crystallizations. Right. Because in a one rock there can be different generations of zircons produced. Unlike the rubidium strontium or samarium neodymium age, where we get only one isochron age, right? But here you can have multiple sets of zircons even crystallized at different time scales. So that means a single rock can be described in terms of their temporal evolution. That means the age evolution by analyzing different clusters or different populations of zircons. Of course, geochemically also we can separate this zircon by using the uranium thorium ratios of zircon, right? So, for example, if you see the uranium thorium ratio, elemental ratio of zircon, right? Uranium to thorium elemental ratio, maybe giving one set of values for this sample and another value for this sample. So that indicates they belong to different generations. They belong to two different stages of evolution. These are formed, right? So this is an advantage in the uranium lead system as well, right? So you don't see any direct graduation there, right? 2 is here, 2.2 is here. So in between you have a star there. So what could be the age there? So you have to do the interpolation. You have to do interpolation. That means in between two known points. If you are deriving an unknown value using two known points away from the point that you want to find, that is called interpolation, right? So these are the 2 points away where you want the edge here, right? So you have known edge here and you have another known edge here. So what you have to do is you have to interpolate this. You have to interpolate this space in terms of age, right? So you can interpolate and take this number 3 as 2.1. It's correct, right? 2.1 is here. Then let's see number 2. It may be 2.7. Yeah, 2.7 or 2.74. This is the resolution. So whether it is 2.7, you stop, or 2.1, 2, 3, 4, 5, 6, whatever it is, right? So the second decimal point is depends on the resolution of your values. That means how tiny spaces you can cover for this interpolation, right, in between. So that is what you call the resolution. So since these type of Concordia curves are supported with Excel or other softwares, we call it high resolution age dating. High resolution age dating, because even for zircons, right, we are measuring zircons for this one, no? You can have very tiny areas, one adjacent to the other, right? So if you can analyze like one point here and another point, This is low resolution because you have huge amount of distance in between unanalyzed. But if you take like something like here, you can analyze very close by areas. So this is high resolution. This is high resolution. So if you hear something like high resolution geochronology, that means this type of very closely spaced geochronological investigation. Right. So for Concordia interpretations, we have to definitely interpolate these values. Okay, this is the Concordia diagram with some examples. And we can consider about the other situation as well now. Right. So you have the Concordia diagram. Previously, you had everything plotting on top of the curve. That means concordant, 100% concordant. But now what you are seeing here, you see your number 3 is here, number 2 is here, and number 1 is here. None of those plot on the curve itself. So to some extent, right, maybe one is very much deviating, the other one may be slightly deviating, right, like that. So this is called the discordance. The amount of discordance is taken as a percentage. That means how much you deviate your sample or the point from the from the Concordia diagram, right? This discordance is also calculated by the software itself or the Excel program itself, because manual calculation is very difficult because you can't calculate precisely this distance, right? But normally the concordance or discordance is given in terms of a percentage. Okay, 10% discordant, 12%, 15%, 100% discordant, something like that, right? But in high resolution geochronology, we tolerate only up to 10% of discordance, right? Only up to 10% of discordance we can tolerate. If anything is more than 10%, you have to ignore that data. You have to discard that data. No use. So that is a standard way. When you are getting these isotope ratios from the machine or from the laboratory, you are given also with these discordance, amount of discordance. Okay. So see, there are 3 discordant edges here, right? So age should be here, right? The graduation should be here. If your sample plots over here, then directly you can calculate. But since it is plotting down there, you can't directly take this number or this value as the age of that particular sample, right? You can't take this value because it is discordant. And also this discordance is, this is not a linear graph as well, right? So x-axis direction, the curve is different, and y-axis direction, curve is different. So all together, the resultant curve is given like this, right? So therefore, calculating the amount of discordance is very much complicated because you don't know how much deviated to x side and how much deviated to y side. This is the how do you call it? This is the deciding factor for the amount of discordance, because 10% move discordance to x side may be like this, and 10% discordance to y direction should be like that. So then your point should be in between somewhere, right? So the amount of discordance in x direction and amount of discordance in y direction will determine the real discordance, the final discordance, right? So that is, and also, these equations are having natural logarithm value e. Therefore, it's very, very complicated. You can't make it as a linear calculation. So it needs some programming in the software. So it's very difficult for us to say that, okay, this is 2.5, or sorry, 2.25, and this is maybe 2.78 or something like that. No, it might be not correct because the discordance is high. If it is very close by, something like here, maybe you can just guess, or you can just interpolate this age as your real age of the rock. But it's now difficult because they are deviated from the curve. So we call discordant values. So interpolation will not work, right, for that one. So, but still, these discordant data are useful for us, right? Although they cannot directly imply an age, the data themselves can be used for us to interpret some other processes, right? We'll see what are the other processes later. Okay, right. So for be useful for dating the uranium thorium lead method, a mineral must be retentive with respect to uranium. That means the uranium should be kept in that mineral or the rock or whatever without exchanging from outside or to the outside, right? So even during decay schemes, during the intermediate decay schemes, you can remember, I think, the intermediate decay should have been kept constant. The equilibrium must be maintained. So usually minerals like zircon can satisfy these conditions. That means many minerals cannot bear resistant to these external exchanges, right? So some fluid may be getting involved inside into the zircon or some other minerals. That makes the data you are getting from this uranium lead system might be unbelievable, or how to say, unrealistic. Okay, right. So but zircon, the mineral zircon, is a very resistant, I mean robust mineral, and also resistant to weathering and other geochemical processes even at the during the interior of the earth. Therefore this is a very good element, very good mineral. This has been experimentally proven also. So this zircon frequently we use for geochronology because of that reason, right? So even zircons can be kept without exchanging any material for long periods of time. So billions of years it can exist. Okay, right. So other minerals include like monazite, titanite, allanite, apatite, xenotime, right? Xenotime, this is xenotime, another mineral. These minerals can be accessory minerals. All these are accessory minerals. So this is another point, important point, right? Accessory mineral geochronology. So zircon and monazite. Also, these minerals are also used, right? So the exchange, the keeping closed behavior is best exemplified by zircons. So therefore, globally, people want to use zircon for uranium lead dating. Okay, so zircon can contain not only uranium and thorium, but also lead as well, right? So lead can also be included there in zircon. So therefore, uh, uranium, thorium, lead, everything is there. So therefore, it's a very, very good field laboratory for our age dating analysis. Okay, uh, this one, lead 2 plus. Lead 2 plus is excluded definitely from the structure, which is the most abundant variety for lead. So that means if you take uranium lead ratio, and also thorium lead ratio, right? You are having tiny amount of lead, but high amount of thorium. Tiny amount of lead, because lead is rejected from the structure. But uranium and thorium are accepted by the structure. So you will have high amount of uranium. So overall ratio, what will happen? If this is very little, say it is 0, for example, then what happens for this ratio? It becomes infinity. It becomes infinite, right? So anyway, the if you reduce lead, your ratio will be getting higher. So in zircon, since lead is excluded from the system, from the crystal, you are supposed to get a high uranium lead ratio and also high thorium lead ratios. So which is very good for geochronology. So remember, for uranium lead or thorium lead geochronology, we need to have high uranium lead ratio bearing rocks or high thorium over lead bearing rocks, right? So mineral can be, right? Zircon is one of those with high uranium lead and high thorium lead, because lead 2 plus, which is the most abundant ionic type prevailing in our samples, that is excluded by the structure, right? It's a structural matter. Maybe ionic potential is different or not matching. Therefore, it can easily be excluded from the mineral. That makes uranium lead and thorium lead ratios are very high, right? Once they are very high means you will have a lot of radiogenic productions, right? A lot of radiogenic productions of lead, because uranium decays, thorium decays to form lead. So you will have a lot of lead produced over time, right? With the time duration. So that is a good point for us. Having a lot of radiogenically produced materials for our analysis. It's very good. If the higher the uranium lead or higher the thorium lead ratios, uh, more better or more precise values for the isotope ratios are given. Okay, some discordant data, right? Like here, there may be discordant analysis giving different ages, right? Some different ages, 1.4, 1.5, or 1.2, right? So this ratio, the star ratio, that you remember, we used it for the Concordia, is giving an age of this much, right? So that means the Concordia diagram will give you this age, right? Because we are dealing with this parameter. The other isotope system, the traditional type of isochrones, like we can have an isochron like rubidium strontium or samarium medium lead. We can have this decay scheme, right? So you will have this age, and this one we have this age. 208 is another age, right? So what is this? So that means for the same sample, different schemes will give you different dates, right? So they are really discordant. They are not giving the same age there, right? So this is sometimes this happens when the system opens, right? When the system opens for uranium or thorium or even for lead, right? This can happen. So if you face it this type of situation, it is recommended that you do some more analysis from different samples, sorry, from different piece of the same sample, so that you can just check whether the previous dates are correct or not. But you know, it may be some difficulties as long as you consider such kind of requirement. But anyway, you can have different ages. You can have different ages there. That indicates some discordance, right? So you will have to exclude those data and do some repeating analysis. So most of the cases, there are so many repeaters. That means once you analyze, maybe you will have to come back in the next week again for checking the analysis, right? Unless if you process it at the lab itself before getting the result out, right? So anyway, lab to lab, there are different protocols, so we have to follow those protocols. We can't do as how we want. Okay, so normally the ages, discordant ages, if you are getting discordant ages, the age will be having kind of an increase from 208, 208, 206, 207, 207 to 206 radiogenic. So this may be like some deviations, discordant data, like what you see here, different ages. You will have discordant ages. Right. So this is very typical for discordant zircon. So therefore, you have to select the correct zircons also, right? That is also very important. You have to study the zircon separately once you finish mineral separation, right? You have to avoid fractured zircons. You have to avoid some reacted zircons. Those zircons, you have to be very careful. So the most easiest explanation is they have not been in a closed system, and it may have caused radiogenic lead to be lost. So if the system is not closed, uh, the lead produced there may be lost. So in that case, when you take this one to the sample, so to the machine, you don't have in the exactly available amount is not there, right? Because it has already gone out. So you are getting a wrong date, right? So that is those are the issues that we face. Okay. Right. So most of the cases, if you are getting some discordance like this towards inside of the curve, right? Discordance is towards the inside of the curve. Sometimes you can have the discordance outside the curve as well, right? So if you have your discordance, like you plot your sample somewhere here, not on the concordia itself, due to some reason, right? It can be due to disequilibrium or opening of the system, which may have caused lead loss or uranium gain, right? Lead loss or uranium gain can give you deviations towards this side, downward deviations. If uranium, uh, this is uranium gain, okay, right? If uranium was lost, because that is also incompatible, if it was lost due to some reason, then your data will be plotting on top of the isotope, right? On top of the concordia, right? So these two type of discordia can be there, right? Lead loss or uranium gain, giving this type of very general type of discordia, and also there can be some uranium gain, uranium loss, that makes everything deviated out from the curve. Okay. So in that case, sometimes this deviation is also systematic, right? Sometimes it is systematic, so that you can draw a line. You can make a statistical line, statistically feasible line. So this this feature uh, will also give you a very important implication. So when you have this line, and if you extend it until you meet with uh, the the curve there, the what is it, the concordia curve there, you can mark that point. Maybe here it is mentioned as beta, and the upper point also you can mark. Here it is alpha. So now your discordia line, if your discordant data are also systematic, otherwise you can't do this, right? If you have very systematic data, because if you have very systematic data means just a one single event has caused this lead loss or uranium gain, right? So you have to draw the as soon as possible the what you call the discordia curve, discordia line, because if you have very systematic data, then you can draw the discordia line, right? And then you can have 2 points which intersect the concordia, right? Naturally the concordia is not intersected, or your samples do not plot on top of this concordia curve. That means your samples must have been in a disequilibrium condition, right? So you have a Discordia plotted, and lower intercept. We call this lower intercept. Lower intercept, and this is called the upper intercept. So you have lower intercept and upper intercept for these Concordia diagrams, right? These are also very meaningful ages you can get, right? For example, this upper intersect point will have something like 3.2 or 3.3 GA like age, and the bottom one you will have maybe like 1.5 or something right here. So you have basically two ages, even with this Discordia, right? We call lower intercept age and upper intercept age. Usually this upper intercept age represents the crystallization age of the rock, right? Crystallization age of the rock, and the lower intercept shows whatever the loss caused event, right? Lead loss, probably most of the cases you will have lead loss because of metamorphism, right? Metamorphism, although it is a closed system behavior, somehow this lead, which is like volatile material, can escape, right? So that will cause some deviation, giving a discordant edges. But still, if those discordant edges are systematic, then you can have an upper intercept and lower intercept, which are corresponding to the crystallization timing of your rock and the time of finishing. Sorry, the time of finishing of this equilibration, or the lead loss, the beginning of the lead loss event, right? For metamorphism, there is a beginning of the lead loss event. That means the finishing time of the disequilibrium, finishing time of the equilibration of that zircon or whatever the material that you use to measure. Okay, so still this Discordia also give you some meaningful time information. So this might correspond to metamorphic age, and this might correspond to crystallization age, or in other words, the protolith age. The protolith age may be given by this upper intercept, and the metamorphic age can be given by the lower intercept. That means if any zircon was suffered the metamorphism, definitely they will be discordant. They will be discordant and uh, get plotted like this. Other zircons, if they are not like discordant, then you can have very nice concordant edges like this, right? So having a discordant edge doesn't mean that you have some problem with the analysis or something, right? No, if you make more and more analysis, you will see the discordia line can be formed also, right? So in that case, two more information is there with the discordia line, upper intercept and lower intercept edges, right? Okay, it's 9:30 now. So we have done 1.5 hours, right? Already? Right. Okay. If you have any questions, you can ask now. Have you put the registration numbers? Okay. Right. So if you have some multiple data, you can plot them, and you will see here very nice spread here. And you can draw a line also. I mean, statistically significant line should be drawn, right? So that you have a lower intercept and an upper intercept, okay, from the Discordia. So what is the age? Age of zircons is given as 3.12. That means this age, right? That the upper intercept age. That means the crystallization age of the zircon, 3.12. The beta corresponds to the age since the lead loss, the time after the lead loss, right? For example, in Sri Lankan rocks, if you measure Sri Lankan zircons, you will see this type of a discordia most of the cases. So it might represent 3 GA or 2 GA as the upper intercept, and the lower intercept is most probably 550 mm, 500 to 550 mm. What is this age? 550 mm. It is also an important age. That is the metamorphic age, right? So the metamorphism is the lead loss event. So that lead loss event made your samples to stay away from the Concordia line, right? So it's kind of an automatic. It's not purposely done, but it's because of natural lead loss you can have this type of discordia. Okay, so the low intercept gives you the age since lead loss. For example, our rocks are uh, like 550 mA. So you get 550 around here, right? You get 550 around here. So that means from today, it has elapsed 550 years, million years after the lead loss event. So lead loss event happened 550 million years ago, right? That's the implication. Right. So this discordia is also, since it is important, so we have some important points to note. So it is plotted on a Concordia diagram and invariably plot either on the Concordia or below the Concordia, because sometimes you might have discordia very close to the Concordia or the Concordia line, right? So there can be discordia, but it's very close to the Concordia. But here you have very distant discordia. So this is kind of a straight line you can fit through and get some important dates, upper intercept age and lower intercept age. So they always remember the lower intercept age represents the lead loss event, right? Lead loss event. But if it is only once happened, that will be shown like that. But if it is like occurring in multiple events, then still you will see this discordia, but the age that you are implying from that discordia may be meaningless, right? Because you don't know how that multiple lead loss events occur. In that case, maybe you have one discordia here, another discordia there, and another discordia there. Like if there has been two or more lead loss events. So these are complicated situations. We are not bothered about these situations at this undergraduate level. So you can consider it as the discordia just a single event. Uh, we can use the monocyte also for the same discordia line might be found. But monocyte being a rare element phosphate mineral, right? It's just a rare element phosphate mineral. Zircon is what? The composition of zircon is zirconium silicate, right? Zirconium silicate. So monocyte is entirely different chemistry. So anyway, so this can show multiple or different uranium loss event can also be shown by these monocyte grains, right? You can remember, I think we mentioned about loss or disequilibration. Can't remember now. Okay. You see here, lead loss or uranium gain is those are the possibilities to lie your points below the Concordia. If it is above the Concordia, most of the cases there has been some uranium loss, some metasomatic effect or something maybe may have happened there, which is called the uranium loss. Okay, right. So if that happens above the Concordia, like if the discordancy is somewhere here, so there will be some extrapolation because we don't have points there. We have points in between so that we can do the interpolation. But if something is there like going above the Concordia line, then we call it extrapolation. Right? It's away from the system or the diagram or what we consider here. right? It's an extrapolation in that case. Right, so this is the Concordia curve, and I will show you some natural examples, a real world example from some rocks analysis. You see here, the only part of the Concordia is given because you see here, it's given in very high resolution. It's 900, 1100, because this spacing makes difficult for the entire Concordia to plot, right? So you will see here 2 and 2.2. The difference is 200 million years, right? 0.2 GA. So that's too much, right? You can't get a precise age. So therefore, based on your data distribution, you can take a portion of this Concordia, right? That is also possible. So this is what you have here. This is from the Ludwig program. So you have some clusters. You have some clusters. So these ellipses represents clusters. So that means different data points, you can have, and you can draw a cluster there, right? Statistically important, these type of clusters. So the mean age is taken, right? The mean age is taken from each of those clusters, right? So you have an age here and also an uncertainty there, right? This is given by the software, and also the statistical significance is also given. MSWD, this value, uh, the lower this value is much better, okay? If it is 1 or below, that will be very good distribution. So you have another mean from the above data set, right? So this may be one sample, this may be another sample, and this green may be another set of sample. Or otherwise, they can be representing the same sample, but different sets of zircons, different generations of zircons, right? That is also possible. So the light blue area gives like 900 to 700 the span. So that is too big. That is very big, and also they are discordant, like unlike the other ones. They are mostly concordant, right? Here also concordant, here also concordant, right? But these ones are not much concordant in its distribution, right? But still a discordia line can be produced, right? You can't see that line clearly because it is constructed there by the software itself. Okay, so this is the Discordia interpretation, like here, right? Upper intercept and lower intercept. This is the normal Concordia plot. This is the normal Concordia plot, right? But nowadays there is a modified version of the Concordia. This is termed as Terra-Wasserberg plot. This is termed as Terra-Wasserberg plot. Terra-Wasserberg plot, because they are the people who invented this the other diagram, right? So to how do you call, to overcome some difficulties in Concordia diagrams. So this is a standard Concordia diagram. There are some difficulties are there because this small difference between the curvature, due to curvature, differences between these curvatures is very hard to consider, right? For example, here you see if you change the curvature, right, here it's different. The interpolation may be very difficult, and here also interpolation is different from this place. So if you want to interpolate some data here, you do that, but the same approach you can't use for this area because their curvature is different, and curvature is different here, curvature is different there. So likewise, there are some difficulties in interpolation. Although it is done by the machine or the software, we have to know the manual way of doing as well, right? So people to avoid this Concordia problem in terms of this interpolation, there has been a new diagram introduced, right? So this new diagram is called Terra-Wasserberg plot or Terra-Wasserberg diagram, right? So this was developed by these two scientists uh, way back in 1970s. Okay, so there what you get is you take this ratio and you take this ratio, right? Instead of you are getting these two, what you get is you take the exact amount that you get from the table. Where is the table? Here, right? Here. So you take this 207 to 206 ratio. That means this ratio, 207 to 206 ratio, is taken for Terra-Wasserberg diagrams to make, right? So you see here, you have that radiogenic component ratio, and you have this 238 or 206 ratio let, and then you make a another curve, right? Plot it, and you will see this type of a diagram. It's very different from the Concordia. Very different from the Concordia, right? So this is called Terra-Wasserberg diagram. This is called Terra-Wasserberg diagram. So remember, for Terra-Wasserberg diagram, we use these two ratios. Okay, right? So the difference between the Concordia and the Terra-Wasserberg diagrams. So these Terra-Wasserberg diagrams are also used in isotope geology for uranium-lead geochronology. Less frequently, yeah, I should say less frequently until like the last year, but afterwards, Wasserberg diagram has been used immensely, abundantly among the community, right? So user friendliness is one of the reasons for that, and also the software has support advanced functions for these ones. Okay, so you plot it, and you have the graduation, which is also very clear graduation. You see, you have enough space there, so that if something is plotting very close by, you can effectively remove or make the, how do you call this resolution wise. The resolution issue can be sorted out very easily because you have enough space in between, right? Unlike in the Concordia diagram, you see, you have very limited space, and also that limits more and more around here, right? So Terra-Wasserberg is very convenient. So in the Terra-Wasserberg also you can have discordia, right? Discordant values, upper upper intercept and lower intercepts. Those two can be there. That also corresponds to the same crystallization age or the lead loss event, maybe the metamorphic event. So these are another application, Terra-Wasserberg diagram, right? Which you can see with the real data also, right? So this is real data, the distribution of data points in a Terra-Wasserberg diagram. You see here, you take this portion separately and see as a high resolution. So you are resolving this data, right? Everything together, clustered, as if like a homogeneous sample or something, but really they are not. See, they have very relative differences in between. So that's why we need high resolution diagrams or using softwares. Okay, so I think up to now you can ask me any question related. I have only a few slides, only 2, 3 slides to finish, because we will see how some analytical protocols are maintained for these diagram constructions as well, right? As I said before, spreadsheets are used. in the Concordia diagram or in a TerraVasable diagram to plot your data. And then we have to discuss about the sample processing, right? We just discussed only about the data so far, right? But to get those data, we need to have proper samples, right? For uranium-lead dating, we use zircons, as I said before, right? But the zircon is also belonging to different generations. You can't mix up everything, even from a single sample. So therefore, you have to do something called CL imaging, cathodoluminescence imaging. CL images means cathodoluminescence imaging. It's a kind of a machine that you can use to understand the internal structure of these minerals, in this case zircon, right? And also we can use thorium uranium ratios to distinguish different generations of zircons, because although you have plots like here, right, you see here different symbols are used. So different symbols means different generations of zircons or whatever the mineral that you use, right? For that you have to use CL imaging or thorium uranium ratios. So CL imaging means it's kind of a structural information given technique, right? There is a machine, actually I should say it's a detector, right? There is a detector that can be fixed with an SCM, secondary electron microscope, what we have in our department, SCM. We can couple a CL imaging detector. We don't have such detector at the moment, but you can fix it. Our machine also can accommodate fix it. Okay, right. So with that, we can understand the internal structure of the zircon. For example, if you have a zircon, whether it is zoned like this. So this part may be unzoned, but this part may be zoned, chemically zoned, right? So maybe also very heterogeneous, very homogeneous zircon. So to understand those different stages of formation, right? These zoning patterns indicate different generations or different stages of generations. There are different zoning patterns as well. We call oscillatory zoning, or otherwise there can be some unzoned zircons like this. Oscillatory means like concentric banding, like concentric bands like zoning. This is very typical for igneous materials. Or otherwise there can be some different embayments or some structural discontinuities, right? So all these internal structures can be understood by CL images. Even overgrowth. For example, if this is a crystallized zircon, if it suffers metamorphism, there can be some new growth on top of that. So that is called overgrowth. So to identify overgrowths also, we can use CL images. Okay, so these are some examples of CL images. You see, this is called the oscillatory zoning. Very beautiful zoning. So you see here concentric zoning at the shape of the crystalline shape of the crystal, right? Here also concentric zoning. This is what we call the oscillatory zone. Oscillatory zone. So these are zircon grains. Zircon grains polished into 50% or the half of its cross section. So this is the cross section you see. Right? These are CM images, secondary electron microscopic images. This is homogeneous type of zircon, right? But still you see there are some fractures, and if you have this type of fractures, that might not be good for dating, because there can be some material exchange. So the isotopic system may not have been in equilibrium condition or closed system behavior, right? So this is overgrowth. You see overgrowth. You have an original zircon here, and it has grown up to here, but at a certain stage a new growth has happened all of a sudden, like very sharp boundary like growth. This is due to metamorphism. Okay, so if you date this sample, That means if you analyze this isotopically here, you will get the age of crystallization of this rock or this cone, and also you will get the age of metamorphism from this edge, right? So this is what we call the high resolution geochronology. So very tiny areas can be measured for isotope systematics. And also you can see numerous types of the cones, how homogeneous, some are homogeneous, some are having some different structures. So anyway, this structural information you can get from cathodoluminescence images, CL images. Okay, different types of zircons are there, right? So here again we have difference. This brightness and dark areas corresponds to zoning, chemical zoning patterns, right? The atomic weight, the atomic weight. If some elements are there with the high atomic weights, you will see some bright areas, right? That corresponds to the atomic weight of each area. Right. So the other thing that we use to interpret or categorization of these different zircons, we use the thorium uranium ratio, right? So internal structure we use, and then we use the thorium uranium ratio. So sometimes thorium uranium ratio is very low for some zircons. For some zircons, it might be very high, right? Actually, the metamorphic zircons typically have low uranium thorium thorium uranium ratios, whereas some igneous zircons have high values. Okay, thorium uranium ratios difference is also very important uh, factor. Okay, so this is how we distinguish these zircons, and then we can categorize them and make separate analysis. So by analyzing them separately, we can get different dates, and then we can interpret them in terms of the geological evolution of the said rocks. So this is what we learn uh, under the uranium lead isotope systematics. Okay, so the advantage here is we have two systems together for uranium lead, and in addition you have another one, that is the thorium lead also, right? Thorium lead also. Okay, so I think we can stop here for today, and you can refresh yourself with uranium lead isotopic systematic readings. So make sure that you read your the said textbooks at the library, because that will give you immense information, additional information, and also a good confident knowledge about the isotope systematics. Okay, so actually I have finished my content to teach with this, but I want another class just to give you some questions, right? We can discuss some questions in a class uh, in terms of all these isotopic systems, right? So we'll have one more class online within the next week. So I will let you know about that timing, right? Most probably you can come to the seminar room and have it everyone together, right? Okay, so I'll stop here for today, and maybe with just one more example class, I will finish all the content. Okay, so your exams are scheduled almost, and you'll be informed soon about the dates, right? That will start from 13th October. Okay, and for seminar presentations, please make sure you get ready with the seminar presentations, and you can first email me, right? You please email me your seminar presentations, and the date of your presentation will be also changing. Dr. Dharmapriya will be informing you about the new date. Okay. So anyway, for those who are doing seminars with me, please send me the so far prepared presentation by email. Right? If it is too heavy, I suggest you to make it a PDF also and compress it and send me. Okay. Right. Okay. So we'll stop here for today. Good night.